आवाज येतोय? आवाज येतोय ना? हॅलो.
Yes, sir.
Dear students, I welcome you for the next lecture related to the jacketed vessels in the subject of chemical equipment design. Today we are going to discuss the different heating and cooling arrangements for vessels. Now in that, the external jackets, external coils, internal helical coils, that is centrally situated, and the internal baffle coils situated on one side. That means towards the one side, then separate or the external heat exchanger unit that can be used. Then electrical heating that is also used. Then the microwave heating that can be used. Photo or the light heating, then ultrasonic heating, and the cavitation heating. So these are the different ways by which we can provide the heating or cooling arrangements to the reaction vessels. Now generally why you require this cooling and heating arrangements? It is basically to maintain the reaction temperature in the vessel. Maintaining the reaction temperature is very essential to get the desired product at the specific kinetic conditions of temperature and pressure. So it is very essential to maintain the desired temperature or fixed temperature at which you get the specified products with minimum side reactions. So this heating and cooling arrangements, they're necessary. In this topic we are going to discuss the jackets and coils in details. Now the jackets, basically the jacket in general terminology, it is nothing but a removable or replaceable protective or insulating cover for an object. This is a general terminology. It's a protective or insulating cover. However, in case of a chemical engineering, the jacket is a cavity external to the vessel. That means to our basic vessel where the reaction that is carried out, you are putting another shell, and that creates a cavity where this heating fluid that will be circulated. Means in between the wall of the vessel and the jacket wall there is an annulus that will be available. Now coming to this figure, basically the jacket, the inner is a vessel and the outer one is a jacket. In between this inner vessel and the outer jacket there is an annular space, annulus that is provided, and your heating fluid will flow in between these annular spaces. So this is a jacket in general case, or in other terminologies, a jacketed vessel is a container that is designed for controlling the temperature of its contents. Basically, basic purpose is to control the temperature by using the cooling or heating media around the jacket. Then also, in other words, the second shell that is installed, it can be termed as the second shell over the portion of the vessel, creating an annular space between the vessel wall and the jacket wall within which the cooling or heating media flows. Now the second figure, that is related to the coils, vessel with heating coil. So the inside there is a coil which is available. The helical coils, they are used. Sometimes they are at the side. This is central coils which you are seeing. Sometimes there can be situated only the side coils. That is what is the internal helical coils centrally situated and internal baffle coils situated on one side. So through these coils, the heating fluid that will be flowing, and which is going to transfer the heat or absorb the heat from the reaction material. Now this is the industrial reaction vessel. To this industrial reaction vessel, the coils which are situated outside the vessel. The coils you can see here, they are outside the vessel. And a single coil is also not there. There is certain intermittent connections which are provided in these coils to properly manipulate the temperature. Now in this process equipment design or chemical equipment design subject, how the symbols are being given the certain specific importance. The vessels generally symbolized like this with a jacket. So they are the symbol with a jacketed vessels. And the second figure, that is with a coils, external coils. If the external coils they are provided, then the symbol will be like this, a simple reaction vessel. Now if the simple reaction vessel, that will be there, a vessel and an agitator that is provided with it. In addition to that, we are providing a jacket or we are providing the coils. So this is a symbol, and these symbols are necessary in understanding the process flow diagrams. Process flow diagrams, they are very important in respect of understanding the process and ID diagram, process and instrumentation diagrams. Basically it's a process flow diagram. Then the instruments are added to that. It will become the process and instrumentation diagram. So the jackets, the different types of jackets used for reaction vessels, they are plain jackets, half pipe coil jackets, and the dimple jackets. Now these are the different figures. Now the first figure, that is related to the plain jacket. You can see the inside one is a vessel and outside is a jacket. So annular space that is formed, and in this annular space the heating or cooling fluid that will be available. Then second, it's a channel. That means a certain intermittent separation that is provided. The separation that is provided to form a channel. The channel can be continuous or channels can be intermittent, and channels can have the different inlets and outlets as we have seen in the upper figure. Then the third one is the tubes. Now the simple tubes, they are welded. These are the complete tubes, full tubes. They are not cut tubes. Then the next, the tubes with the copper strip. The copper strips, connected copper strips, so that the heat transfer will be increased. Copper is a good conductor. So the copper strips, they are welded through the copper strips so that the heat transfer will take place in a better way. Then the next is a half coil. That means a pipe that is cut into the two and then it is welded to the vessel. So it is a half coil. Then next is the overlap cut coils. These are the overlapping of the cut coils. Then next is a dimpled construction. So certain dimples, they have been provided intermittently the dimples that has been created so that the heat transfer that will be enhanced. Now in understanding this jackets and coils, basic requirement of heat transfer that is also essential. Then the these plain jackets, they are generally preferred for small capacity vessels. They are preferred for small capacity vessels where the inside pressure is more than twice the jacket pressure. So it is more suitable for heating purposes. That is, and even that heating purposes, the fluid that is used is a steam. Then the jacket height is usually up to the liquid height in the vessel. That means L by D, that is to be considered when we talked the vessel length to vessel diameter, that is generally L, which is equal to the D. That means the diameter of the vessel, only that height we are maintaining, the liquid height we are maintaining. So liquid height inside the vessel, there up to that height only the jacket height that is provided. That means the jacket height is usually up to the liquid height in the vessel. Jackets can be fabricated in one piece or can be divided into the number of parts or certain segments or baffles that can be provided. Now this is again the plain jacket, that is enlarged view that is shown. The plain jacket, welded jacket, to that the nozzle that has been provided for the inlet and the outlet. This is the complete view that can be observed. The next is a ring that is provided. How the jackets, they are attached to the vessel, that is by welding certain rings or the direct welding for the vessel that has been done. Here the bending that is also incorporated and then welding that has been done. However, here the ring that is provided, and to that ring the second shell that is provided. A simple conventional jacket with no internal components. Generally it is the no internals, that means no baffles or no separators they are used. In general it is very inefficient for heat transfer. To create a better heat transfer, you require to create the turbulence, or the velocity should be high. However, the jackets without internals can have a very large volume, and once the volume is large, so velocity that is drastically reduced, and as a result the heat transfer coefficients are low, inefficient for heat transfer because of the low velocities resulting in the low heat transfer coefficient. Then in this figure you can see the vessel with internal baffles. You can see the baffles which are available in the jacket. Baffles which are available in the jacket. So that is going to create the turbulence because the velocity that is decreased when you are putting the reducing the area by putting these baffles. So you are trying to maintain the higher velocity. As the velocity is more, the turbulence will be more, and as a result the heat transfer coefficient that will be the more. Then how the half pipe coils they have been created. Then pipes are split lengthwise. That means a pipe that is cut into the two parts, usually at 180 degrees or 120 degrees for overlap. Then it is welded around the vessel. These pipes provide the high velocity, which incorporates the higher turbulence as the cross sectional area is reduced in the pipes. So the velocity will be high, turbulence will be high, and that is providing the higher heat transfer coefficients. Not only that, these welded half pipes they provide the strength to the vessel, they provide the strength to the shell. So these half pipe coils they act as a higher strength provider. That means it can be incorporated at a higher pressure. थिकनेस इंक्रीज हो जाती, स्ट्रेंथ इंक्रीज हो गई, थिकनेस इंक्रीज हो गई. It provides the structural rigidity also, which is an advantage for higher temperature. Here the half pipe coils they are welded. These are the overlap cut coils are welded, which are cut at 120 degrees. These are 180 degrees cutting. Then half pipe coil jackets are usually made from carbon steel, stainless steel, monel, inconel, and sometimes copper or nickel. Now they are used for high capacity vessels where the higher velocities for circulating the hot fluids that is required. Then third one is a dimple jacket. A thin external shell is affixed to the vessel shell with spot welds located in a regular pattern. That means, look at this figure. You can see the certain welding to the vessel that is observed, like the pimples. These dimples they are also there, that is forming a regular structure. These are small or thin plates and welded regularly to the main shell. So it is used for high jacket pressure operations. Dimple jackets can induce the turbulence because these are welded, so your area that is decreased, sometimes the area is more, sometimes the area is less, so that is going to create a turbulence which is incorporating the higher heat transfer coefficients. It can be used for circulating steam, hot oil, Dotham vapors. So here also you can see the actual dimple welded to the vessel wall. So certain grooves that has been created and they are welded. So again these are the heating and cooling coils with the limpet. Now coming to the comparison between the coils and the jackets. Generally the jacketed vessels they are used for the smaller dimensions where the steam that is used as the heating media. Then more heat transfer, amount of the heat transfer is more, however the heat transfer coefficient is less. More heat transfer amount, when you talk the amount of the heat transfer that will be the more, However, the heat transfer coefficient is less in case of jackets because there are less velocity. Similarly, the pressure drop is also less in jackets, but the channeling of the medium is also possible in the jackets unless the spiral baffles are provided. Pumping cost is low as the velocity is low, so pressure drop is less, and as a result the pumping cost is also less. However, for the same operating pressure, jacket requires more thickness than the limpet coils because the coils itself provide the strength. Then construction of jacket is easy in comparison with the limpet coils because for limpet coils you have to cut the pipes, you have to weld throughout, and this welding throughout that incorporates the additional cost. Each coil that is to be welded, so that is not easy job and that is not a cheaper one. So fabrication of the jacketed construction vessel is easy as well as it is cheaper. However, it provides the more surface area also. That is why amount of the heat transfer is more. Surface area is more, so the amount of heat transfer that will be the more. Then limpet coil pressure vessels are extensively used in process industries if the external pressure is the deciding factor. That means when the external pressures are higher, then these coils, half pipe coils, they are used. Then for batch heating and cooling operations with limpet coil, it can be assumed that the thermal conductivity, density, heat capacity and heat transfer coefficient remains constant. These are the assumptions for calculation of the heat transfer coefficients in the coils and jackets. Then vessel wall is thin so that the temperature gradient across the thickness can be neglected. A uniform temperature that is considered, or we can say the resistance created because of this vessel wall that can be neglected. No heat losses to the atmosphere, that means it is perfectly insulated. Then batch fluid temperature is uniform throughout the vessel at any point of time but varies with time. Then there are design considerations that can be taken into account. So these are the different figures associated with the jacket attachments to the vessel. Bottom outlet in a pad welded and head and jacket. Now, when we consider these heating arrangements, one additional thing that is required, that is the heating fluids. So you require the heating fluids to heat these jacketed vessels or coils. So generally the hot water that is used, which is the most cheapest, cold water that is used for cooling purposes. Then steam, molten salts, flue gases, diaphragm, thermic fluids. These are the different types of the fluids that can be used. They are having a temperature range. Which temperature, depending on the temperature required, I am going to select the type of the fluid. If it's a water that is used for cooling, means cooling from 50 degrees Celsius to 40 degrees Celsius. So I am going to use a cooling water. Then if I want to heat the hot water, I can go up to the 100 degrees Celsius. If it is more than 100 degrees Celsius, then steam that will be used. And if it is more than 200 degrees Celsius, then it's a diatherm or thermic fluid, 200 to 400 degrees Celsius. For steam, I can go for higher temperature also. However, the required pressure that will be increased. So managing with the higher pressure becomes more difficult, and it requires the thick material because the pressure that is increased. So it is better to use the steam up to 170 or 180 degrees Celsius, which is up to the 15 kgs or 20 kgs. Then it is better to use the diatherm or the thermic fluids. Again, that depends on the availability in the plant. If I am having only steam, then I can prefer for higher temperatures, higher pressures and higher temperatures. But if the diatherm or the other thermic fluid that will be available in my plant as the utilities, then I can preferably select the diatherm or heating fluid from 150 degrees also. Then the molten salts, they use at a higher temperature, that is 400 to 600 degrees Celsius, 700 degrees Celsius. Then the flue gases from the chimney stack, they can be used at a still higher temperature, that is 750 to 1000 degrees Celsius. Then what properties of this thermic fluid they are preferred? High thermal conductivity, stability, low viscosity, high density, less corrosive, and the lower cost that is needed as the properties for heating fluid. This is the steam, which is one of the most effective heat transfer medium used in the industry. Steam, that is the cheapest one. Hot water, that is still cheaper. Again, that depends on what temperature that is needed. Then the advantages of using the steam: higher thermal conductivity, low viscosity, easily available, and more economical. It's a pure source. Then steam is used as a heating fluid in the heat exchangers, reactors, etc. Next is the thermic fluid. The thermic fluid is the hot fluid. Oil selected should have the following properties. It should have be thermally stable, oxidation stability, temperature stability, as well as the oxidation stability at a higher temperature. Then low viscosity index, then low volatility characteristics, good corrosion prevention properties. Then the advantages of thermic fluid over the steam: used at a higher temperature, higher efficiency, low corrosion problems, low maintenance cost, and environmental safety. Then the molten salts. The salts, they are at a higher temperature, they attain a liquid state, and these liquid salts, they are used as the heating media. They are generally used at a higher temperatures, 400 to 600 degrees Celsius. Then chlorides, fluorides, nitrites, salts, they are generally used. But again, these salts are having the restrictions: less pollution, non-flammable, abundantly available, less vapor pressure, do not degrade over time and hence not needed to replace. Repetitive cost is less. Then Dowtham. This Dowtham is one of the most commonly used. This is the DuPont manufactured. It is a eutectic mixture of two very stable organic compounds, that is bisphenol and diphenyl oxide, which is in proportion of 76.5 and 24.5 percentage. Bisphenol and diphenyl oxide, they are used. Then Dowtham may be used in the systems employing either the liquid phase or vapor phase heating above 100 degrees Celsius to 400 degrees Celsius, that is preferred. Thermal stability, low oxidation stability, low viscosity, non-corrosive, good thermal conductivity. Flue gases is a combustion of the exhaust gases produced at the power plants or boilers. It mainly consists of carbon dioxide, oxygen, nitrogen, along with some amount of carbon monoxide and methane. It contains large amount of heat due to which it can be utilized as the heating fluid. So we are reducing the flue gases temperature by incorporating the heat exchanger and reducing its temperature. Devices like boiler, heat exchangers removes this valuable thermal energy from flue gases to preheat the feed water, process water, combustion air. For these purposes, these flue gases, they are generally preferred. Then nowadays, the nanofluids, they are also coming into the picture. These are the fluids containing nanomaterial size particles of metals or their oxides, or sometimes carbon nanotubes, they are also used, but they are very costly. So ineffective, that is under the process of research. Effectivity, that will come in time. These particles are suspended in base fluid like water or some organic solvents. However, they are having the higher heat transfer coefficients. Higher heat transfer coefficients, high thermal conductivity, good stability, reduced chances of erosion, then reduction in pumping power. These are some of the advantages. Now the applications in case of your heat exchangers, domestic refrigerators, nuclear reactors, coolant in grinding, in solar collectors, in boilers. Then similar to Dowtham, it's a paratherm also. That is a paraffinic hydrocarbon. Dowtham is a diphenyl oxide and bisphenol. In paratherm, it's a paraffinic hydrocarbon based heating fluid system that is used. Paraffinic hydrocarbons. It is classified depending on paratherm L, paratherm HR, NF. So different types that is available and can be used for different temperatures. LR is for lower temperature, MR is for middle range, like that. Then therminol, that is also the another thermic fluid which is commonly used in the industries. Therminol, it is a synthetic heat transfer fluid. It is a mixture of polycyclohexane and bicyclohexyl. Polycyclohexane and bicyclohexyl. So it's a synthetic heat transfer fluid. Again, it is having the different types depending on its temperature used. Therminol VLT, very low temperature, LT, lower temperature. Depending on the temperature, these nomenclatures, they have been provided. Now what are the properties of therminol? That is the fouling resistance, low viscosity, high thermal stability, long life, effective performance, high thermal conductivity. Then applications of this therminol: natural gas purification, asphalt storage, biodiesel industry, chemical process heating, plastic molding, oil and gas industry, synthetic fiber production. Then Dow frost. This is also mixture of propylene glycol with water and some amount of the dyes and corrosion inhibitors. Dow frost. So Dowtherm, Dow frost, thermic fluid, therminol, they are the commonly used thermic fluids. Then cooling fluids. Then brine less than 8 degrees Celsius, chilled water less than 35 degrees Celsius, cooling water in between 35 to 100 degrees Celsius. Then sometimes oils which can be used at a higher temperature, air that can be used at a higher temperature more than 60 degrees Celsius. So these are the cooling fluids. They are also important. Brine, chill water, cooling water, oil and air. All these are the cooling media. So this is all related to the this is all related to the jackets, their heating arrangements and the heating fluids.